How are the challenges of geotechnical uncertainty identified?
For me, so how was my journey? How I realized that we had a problem in terms of geotechnical uncertainty was back to my time doing research in my former university at UPC in Barcelona, Spain. So basically at the time I was working with numerical modeling. So basically mathematical predictive models, trying to predict how the ground is going to behave, how the ground is going to interact with the structures that we are building for building our new infrastructure. So the thing is, we were using really sophisticated tools like Plaxis, adding complex geometry, complex equations, and we were doing really good predictions. But then we realized that during construction, we had a lot of data from IoT sensors that were actually giving us the real response of the ground. And the reality was that they were not matching. So the predictions and the real response from the sensor were not the same. So at that point, I realized that you can create your best model, but if you cannot reproduce what you are seeing from the sensor, you have a problem. And then I realized that if you are not using good parameters in your models, you are not capturing the reality. So that was, for me, the beginning, when I realized that's geotechnical uncertainty, and geotechnical uncertainty, it's really impacting us on how we predict the ground is going to behave.
So what breakthroughs in theory or knowledge resulted in the application of machine learning to geotechnical model enrichment?
Nowadays, with all the computational resources that we have available and we have access, we can actually predict and simulate really complex physical problems with our computers. The thing is, by increasing complexity, you are increasing the number of parameters that you need to determine inside your equations. And that's making more complex to do the definition. So once you are working with one parameter, it's easy to assume some assumptions and then put some values and get some results. When you are dealing with tens of different parameters, you need help. You need some kind of artificial intelligence, some digital tools to assist you as an engineer to understand all the relationships between parameters inside your predictive models. Because sometimes, even though in my case I'm a geotechnical engineer, we are using really complex modeling with really big equations that many of those parameters inside, they don't have geotechnical meaning. They are purely mathematical parameters. So it's really difficult to give meaning to those parameters. So those artificial intelligence, machine learning algorithms are helping engineers to make some meaning and some connections and interaction between these huge number of different parameters that we need to do better predictions.
All right, thanks. I think that was a great explanation. How are gains of model enrichment quantified?
So for us, the biggest gain or what we are solving is reducing uncertainty. And that's vital and that's extremely important. What is at the end uncertainty? So basically, you are trying to reproduce a physical phenomenon with some equations, which at the end are a simplification of the reality. So you need to make some assumptions and then introduce the value of those parameters inside those equations. So we assume, and that's the theory behind all the inverse analysis that we are using to adjust numerical parameters or calibrate numerical parameters. What we are assuming is those sophisticated tools are perfect, which is not true because they are simplifications, but also that all the data that we are using to calibrate those models are good and it's enough. We have good quality and good volume of data, and that's not also true. So basically, we are saying that all discrepancy between predictions and reality, it's because the parameters. That's a huge simplification, but that's geotechnical uncertainty in some way. So What we do, or what we try to accomplish, or what is the impact of geotechnical uncertainty, is trying to put the right parameters representing the physics to make sure that your simplified model can predict the reality. And that's not an easy job to do.
Okay, so can you describe a little bit about what like the field work was like? Were students working on construction sites? Can you put a picture to that, please?
I will give you the example using myself. So it's quite typical, or at least here in Spain, when you are doing research, you are doing your own research, but also you are doing many other things. Especially if you are doing research in a technical university like the civil engineers university, sometimes universities work as consultants for big projects. So in my case, and I think that that's quite common in many countries, researchers are working as specialist consultants in big infrastructure projects. And that was my case. So part of my job was doing my research, working with numerical modeling, creating a software to calibrate those models, but then creating models for the industry to design the structures, to design the construction procedures. And then I try to match those two worlds as a researcher using new technology in the industry and trying to bridge the gap between those fields. And you can find students doing research, working as a consultant, making or putting a lot of hours and effort trying to test new technology in real projects. And that's really important. That was my case. I was doing my research, testing part of my research in a real project and working as a consultant too. And then seeing that it was a problem regarding geotechnical uncertainty that we could solve with some research that we were doing at the time.
Okay, so that's covered a lot of the academic aspect, but at what point did you realize that these theoretical insights should be brought to market to benefit infrastructure?
I think that, I don't know if it was a specific day, but I remember like working in a big project here in Spain. It was the time when we were building the high-speed train connecting Barcelona to the border of France. And I was doing a lot of modeling, a lot of models, a lot of hours doing modeling, using really fancy equations, big models, complex geometries. And then I was also analyzing all the data from the sensors that were installed on the site. And at some point, I was realizing I'm spending hours and hours doing those models, but they are not capturing what the sensors are saying. So I just started like doing manual calibrations, just trial and error, like trying to change some parameters to see if I could match what I was seeing from the sensor. At some point, I realized, wow, that's extremely time consuming. We need to create an automatic methodology to connect modeling with data. And that was what I did as my PhD. And then I realized Spain is different than the States, where universities are willing to bring technology into the industry. When I realized the need to bring some research into the industry was at the time that I was working as a consultant, because it was the time where we were building the high-speed train from Barcelona to the French border in Spain at the time. So I was spending a lot of time doing modeling, trying to reproduce the ground behavior, doing calculations, but also analyzing data from sensors. And at that time, after spending so many hours doing modeling and seeing that my models were not reproducing what we were seeing from the sensors, I realized that we need to create a technology to connect those models with the data to actually calibrate in a real-time manner, to actually predict and impact a project. So that was the time when I realized this research needs to go to the industry with a platform connecting those worlds, the modeling and the IoT data. My name is Cristian de Santos. I'm the CEO and one of the co-founders of SAALG Geomechanics. I'm a geotechnical engineer. with a PhD in soil mechanics. So previous to founding SAALG Geomechanics in 2016 with Ignacio Aligué, which is the other co-founder, I was doing research for more than 8 years in my former university, UPC at Barcelona, mainly working on medical modeling and trying to calibrate those models with monitoring data. At SAALG, I'm responsible from the strategy, the management, as well as implementation of our software, Darwin, which is a technology based on machine learning algorithm that is connecting numerical models with IoT data. And that's who I am.
So why is machine learning the right technology to apply to geotechnical uncertainty? What metrics have been developed that establish the validity of machine learning insights?
Why we are using machine learning? I think that the answer of this question is because the big volume of data that now we are generating in our projects. We love to install sensors. There are a huge amount of data, and it's really difficult to make sense to all this data. So I think that machine learning algorithms are a good technology or methodology to make sense to all this huge amount of data. I know there are different technologies, artificial intelligence, machine learning algorithms, genetic algorithms, or whatever you want to call it. Some of them are similar, some of others are a bit different, but at the end is something that help engineers to deal and analyze huge amount of data. And specifically in geotechnics, we had huge amount of data. And sometimes it's really difficult to deal with this data, with this huge uncertainty. So these technologies absolutely are something good that is helping a lot.
So you just kind of talked about genetic algorithms, machine learning, and AI, and large language models. Can these terms be usefully distinguished? And are some more appropriate for use in geotechnical applications?
Wow, that's a tough question. As I said before, like there are many different names for similar things, and also there are similar names that are completely different things. So here, sometimes I'm struggling when I'm saying what kind of technology sometimes we are using, if it's artificial intelligence, machine learning algorithm. So that's a really difficult one. At the end, what we really think that we need is a technology capable of linking huge amount of data, and all of those technologies that you are mentioning are doing that. So apologies because I don't think that I can answer properly this question, but that's the reality that we are facing. Many people, including myself, we are using those terms in a wrong way many times.
So is the basic idea of applying machine learning to sensor and sample data derived from work in other disciplines?
Absolutely. I'm all the times like saying the same because at the end we start our journey focused on geotechnics, but at the end what we are doing is connecting predictive models with data. You can pick whatever field you want. You have predictive models, you have data, so the methodology is exactly the same. So you can extrapolate this calibration methodology or this connection between predictive models and data to all different fields, economics, other fields of science, whatever you want, absolutely.
So would you say that your work is likely to extend and augment the use of spreadsheets or eventually replace spreadsheets entirely?
I have to confess, and I'm not embarrassed, I'm using Excel spreadsheets a lot. But the thing is, with a spreadsheet, you are flexible, you can do whatever you want. So that's part of the reason why we are using a spreadsheet. But the thing is, what we are doing now with this connection between models and data, and especially because we are creating a tools for geotechnics, created by geotechnics, we are doing something that is helping me to use less Excel spreadsheets. But the reason of that is because what I said, we create a tool for geotechnics created by geotechnics. And that's not so common. Usually you have software developers doing really nice job, doing software, but they are not the natural users of their tools that they are developing. And in our case, we create our software because we wanted to use something different than Excel spreadsheets. So yes, I expect to use less Excel spreadsheets in my future.
So as you've now moved to practical applications, have there been lessons learned that have modified theories and or new knowledge about geotechnical uncertainty in practice that has extended or confirmed the theories?
What's clear is thanks to data, we can prove that models are a simplification and have many limitations. Sometimes you cannot give an answer what is the problem, but knowing that you have a problem is extremely important to be aware. So one of the things that we can prove now is the limitations of numerical modeling, as well as the quality of the data that we are using. And then once you realize regarding limitations and quality of data, you can use them all together to really predict what is going to happen. And then by having the possibility to kind of predict future, you can change, you can optimize, you can detect instabilities. So you can evaluate possible future scenarios regarding earthquakes, flooding, or whatever you want. So yes, that's the kind of thing that we can do.
My name's Alan Jones. I'm a senior director with the Solution Engineering Group of Bentley. My area of responsibility is data from IoT sensors. My background, I've been involved in geotechnical and structural instrumentation for the last 30 years, started life in the UK, installing instrumentation on highway embankment settlement monitoring and then tunnel monitoring in the UK, and then moved to North America back in 1996. And I've been involved in instrumentation and monitoring projects across the world, from slope stability to environmental to pipelines, bridges, tunnels, dams, you name it. I think I've probably been involved in it from an instrumentation perspective. So that's me.
Is this a novel approach that only applies to geotechnical uncertainty, or will it make its way into other disciplines such as seismic monitoring or mining applications?
As I said before, the thing is you can apply this connection between modeling and IoT data to all different kind of disciplines like mining, seismic analysis. The only thing that you need is a model and data. So of course, that can be extrapolated to everywhere you want to apply this technology. And the good thing is we are having data from everywhere, minings, different civil infrastructures, different areas, and we really have powerful modeling tools to actually reproduce complex physics phenomena. So yes, you can do that with no problem.
Yeah, I would agree with Cristian there. I mean, from a modeling perspective, certainly the world is split between everything in the ground and everything above the ground. So from a geotechnical perspective, it's certainly a well-established discipline. The connection between IoT sensors or real-time data in the field to the model, we've done a couple of proof of concept projects, but from a technology delivery perspective, I see integrating that into a common workflow in the future, right? That a client will be able to connect their model to their data simply and in a straightforward manner, and be able to drive additional information about the performance of their asset. And that is true from a geotechnical as well as everything above ground. So a structural perspective, as long as we can model whatever it is we're monitoring, that we can drive those analytics using real-time data as well. And mining is very much the same. I mean, mining is pretty much geotech, right? It's subsurface or it's open pit. So we're talking about stability analytics. And as Cristian said, if we can model it, we can make predictions about the performance of it.
So please provide an overview of how geotechnical model enrichment is applied during infrastructure project lifecycle phases from pre-planning to operation. In particular, do you expect your work to be useful for owners, operators, and how?
Here, the thing is, if you see the whole life cycle of a project from planning, designing, construction, and operation, there are many different data that you have available. There are different information that you have at the time. So there are different things that you can do on the different stages of a project or infrastructure. How we envision this workflow or this journey is first starting during the planning stage using historical data that can be geotechnical reports, boreholes, laboratory tests, in situ tests, or even IoT data from historical projects in the area. This information can help you to define your geotechnical campaigns during planification. Then you go to design stage where you have some idea about the ground conditions, and then you start modeling different design options. There is no data from your current project because you are not constructing, but you are playing with your hypotheses, your designs, your modeling. So here you can start analyzing what is important in terms of the influence of each parameters in your model. Then you have your model, and then you go to construction, which is the moment where you install your sensors, you start gathering the data, and you start comparing your predictions based on design hypotheses with all the data coming from your sensor. And then you see if they match or they doesn't match. If there is a match, you were lucky, you got good hypothesis, you make good predictions. So you don't need to change, or there is no room for improvement because you already match what is happening. If there is discrepancy, is when you start proactively analyzing all the IoT data with your predictive models until you match what you are measuring at the moment. The good thing is you calibrate the model in the early stage of construction. You predict what is going to happen in future construction phases of your project. So you can detect instabilities. If ground is better, you can excavate faster, you can reduce the number of props or whatever, but you can anticipate, you can optimize, you can be more efficient, and at the end, you can reduce CO2 emissions because you use less material, you go faster or whatever. And then once you are on operation, if you are still, and that's important, if you are still using and analyzing the data that are coming from your IoT infrastructure, you can keep enriching your model to analyze future possible scenarios. What happens if an earthquake is coming? What happens if a flood is also coming? So IoT data in real time during operation can help you to detect any kind of instabilities in advance. And then all this information is going to go to historical information for future projects. So you are closing the loop from planning, designing, construction, operation, go back again to historical data.
The challenge that owner operators tend to have is that there generally is a disconnect between the construction and operational phase of a project. And instrumentation that's installed at the construction phase is often not used during the asset management phase. Like we're talking about construction monitoring as opposed to long-term structural health monitoring or asset lifecycle monitoring. So the idea of Bentley's iTwin model concept is that we can warehouse data from site investigation, borehole logs right at the beginning of a project, and all the instrumentation data, all the modeling information, that gets transferred to the asset owner so they can utilize that information as part of their long-term asset management. So whether it's a bridge that they're seeing some geotechnical challenges in the foundation design, that they can then refer back to the original borehole logs, that this central repository of information about the asset that we're building plays a significant role in overall reduction in the overall cost of that, because they're not having to go and dig out documentations and drawings that have existed for the last 20 years are in a document folder in an old drawer somewhere, but it's all centrally located. And so, from a mining perspective, we like to think about, from the greenfield to the greenfield at the other end, right? From the asset being built to the asset being restored, or the ground being restored to its original condition after that process has occurred. So the full life cycle of it.
Yeah, if I can add something also, the good thing of this connection is that all the different agents involved in a mining, in an infrastructure project, like the designer, the contractor, the asset owner, all of them are getting benefits. For the designers, they are using better tools, more information to deliver leaner and better designs. From the contractor point of view, they can reduce cost, increase safety because they are reducing geotechnical uncertainty. And from the asset owner, you are reducing risk. Of course, always you have the option of reducing costs, being more efficient, but safety for asset owners, it's vital. And this proactively approach to analyze data, it's vital. If you see now how we are using data, many times it's just comparing data with some kind of thresholds, but there is no proactive approach to keep analyzing data all the time and enriching our modeling. And that's what we are doing by connecting IoT data with modeling, this proactively analysis in real time. That's a key point of this methodology and technology.
Very much so.
So what is the state of integration with BIM? Are you seeing any potential use with augmented reality applications?
So from my point of view or my end, yes, there is potential integration because at the end you are modeling. Again, it's a simplification. A BIM, it's a closer view of the geometry of the reality, which at the end, combining all this information, modeling, BIM, data, you have your actual digital twin, okay? From our perspective, from SAALG, we would like to include BIM as a way to keep track what is happening on the construction site or in the infrastructure, to know when we can compare our modeling with the data. Because as I said before, modeling is a simplification. So every day, many things are happening on a site. So not all the data can be compared with the model. Not all the data can be used to calibrate the model. So BIM can give you full visibility what is happening every day with really detail. So yes, it's really important to integrate it with BIM to actually go for the full smart and clever digital twin, which is the future. Everything is going to be digital, and the digital twin is the representation of the reality in your computer.
Yeah, I agree. Certainly the adoption of BIM or digital twin is a slow process, right? I think most industries have a inertia when it comes to change, and lots of people like 2D models and 2D plans, but people have been building cars and building airplanes for decades using the equivalent in their sector of BIM. The construction industry, we're seeing a greater adoption of it, but it's still a working process. The value of it is often a challenge to demonstrate or to articulate, from, as Cristian said, from both an analytics perspective and a long-term use perspective, right? Of we have a central high fidelity model of the asset that we're building, and it reflects not only the design but the construction, and that's of tremendous value. But again, we still have a contractual disconnect between construction, design, construction, operation, and maintenance, right? And we need to provide that connectivity to really to realize the overall asset of digital twins.
So now on to a little bit of some prediction questions. In 10 years, how much do you expect geotechnical uncertainty to be reduced in large infrastructure construction?
I hope a lot, because we will be including huge amount of data in our models from historical projects. And at the end of the day, we are doing similar projects everywhere. So if you analyze historical projects, you are going to get a similar response in your new projects. So of course, by adding and analyzing data, you are going to reduce uncertainty a lot, with no doubt. But we have a long journey regarding analyzing data, and especially how we connect all the data and who is the owner of the data. And that's really important, because here sometimes in one specific projects, you have the company installing the sensors, you have the contractor sometimes paying for those sensors, but then you have the asset owner paying for everything. And sometimes who is the owner of the data? Who wants to share this data? And it is extremely important that at some point we are willing to share this data for the good of the industry. And that's going to be a real challenge. I think that the biggest challenge in construction is not a technological challenge, it's how we implement technology, how we share data, and how we try to improve the industry as a whole. And that's really the challenge, the willingness to share data, to make data available to everyone.
I wholeheartedly agree, Cristian. I mean, I fully expect that in the future, uncertainty is going to be significantly reduced by the simple connectivity of data in the field and models. Right now, it's an overly complex process, and so the adoption of that is quite limited. And the simplification of that process is going to drive adoption. But in echoing your other comment, Cristian, of the availability of monitoring data, that is a significant obstacle to this process. And I speak from some experience in this field. We look at these large urban transportation projects that are going on throughout the world, where millions and millions of dollars is spent on instrumentation alone. And I was in Europe a few months ago, talking to instrumentation companies and asking them, well, where's the data for this project, right? And they all sort of laughed and said it's in a dusty laptop in a drawer somewhere, right? And that's quite alarming, because, you know, quite literally the contracts that are doing this instrumentation on these large are millions of dollars, tens of millions of dollars is spent on instrumentation on these large infrastructure projects, and the data are just lost. And so, agreed. We need a contractual obligation to future-proof that data, right? It needs to go somewhere that it can be accessible to other stakeholders but in the future, right? So we can leverage that data, because large language models are nothing without data. And the more data that we can put into those models, the more valuable that large language model will be. And if data are stored in a dusty laptop in a drawer somewhere, there's no value in that.
And the worst thing is, many of this data is from public projects paid with public money.
Public money,
so
yeah.
that should be available, 100% sure, from my point of view. And
Absolutely.
that's a pity how we are not asking for our data that we have been paying with our taxes.
There's also a contractual side of this, Cristian, which has been argued for a long time, right? And it's you know, who pays for it and generally dictates who owns it. And so, you know, if it's part of the, you know, if it's a supportive excavation and they're they're instrumenting that as part of the construction process. Well, that data are owned by somebody else, right? But we need to have a contractual process where that data are made available to the public.
Okay, so also looking to the future, are some projects or even entire construction types likely to become more feasible largely due to reduced geotechnical uncertainty?
At the end of the day, if everything is built on the ground or under the ground, and by knowing better how ground it's going to behave, you are opening the possibility to do almost everything you want. But the reality is actually we are doing almost everything. The only thing it's, I think, in my opinion, many times in those big infrastructure projects, we are paying too much in terms of financial cost as well as environmental cost. At the end of the day, you can use your safety factors and start putting concrete, putting more steel, and it will resist for sure, but that's not engineering from my point of view. Engineering is doing everything you can with the right amount of resources. If you have less resources, everyone can build a tunnel, a bridge, or whatever. So, of course, this reduction in geotechnical uncertainty, this connection between modeling and IoT data is going to help us to do real engineering, not just putting concrete and putting steel on the ground.
Over engineering, right, Cristian? It's over engineering. I mean, I don't believe, all we have to do is look at the past to see the scope of some engineering projects. I mean, in my early lifetime, the Channel Tunnel connecting England and France, I mean, that's just, good Lord, we would take a step back today and go, how are we going to do that, right? There's so many engineering challenges, and that was 40 years ago. We just have to look at the Golden Gate Bridge, the Hoover Dam, to see some of these massive construction projects to realize that we can do it right now. But as Cristian was saying, the cost of doing it, we can significantly reduce the cost by utilizing instrumentation to compare our model to the reality, our predictions about overall performance, so that we can tweak the design during construction, or even leverage data from typical or similar projects and utilize that in our design. So yeah, it's cost reduction. I don't think our ability to dream big in terms of construction projects, that's not going to go away, and it hasn't changed significantly over time, but it's our ability to drive the value and reduce the cost of those projects that will be driven by this technology.
Absolutely. And one important thing is we need to make sure that we change the idea that monitoring data or installing IoT infrastructure is a cost, is an investment, a clear investment that will reduce the cost of our ongoing projects and future projects. That's clear. And sometimes this selling pitch is difficult, but for me, it's clear from the first moment. That's investment. That's how you can do better engineering, by having data to make and take better decisions, for sure.
Do you think you guys could elaborate a little bit on the over-engineering aspects and perhaps provide some examples?
A very classic use of instrumentation is during construction for the support of excavation, right? So people are digging a foundation and they're supporting that excavation through a variety of techniques. Tieback anchors are a common one, and the spacing and length of those tieback anchors are dictated by the geotechnical engineer, the person who's designing that SOE structure. Well, we can use instrumentation, and has been used very successfully in real-time adjustment of that supportive excavation. That using monitoring data, we can see how well that support design is performing, and we can modify that design based on that data. And there's many, many cases of this being used, and it's a very common form of feedback. It's From my perspective, it's the most common form of feedback, because we can, these supportive excavations are done in layers, and so we can monitor as each layer is happening and modify the design as we progress, saving millions of dollars on the overall delivery of that. That's part of the scope. So that's a classic example from my perspective.
Actually, there are methodologies already implemented and included in some kind of contracts. So you can find what is called the observational method, where you start with a conservative design, assuming the ground conditions that you get from your geotechnical report, all your boreholes, laboratory tests, in situ tests. So based on those conventional analysis, you define your conservative or your primary design. Then you start playing like with your modeling, playing with changing some hypotheses to see what happens if I increase the stiffness of the ground. Can I reduce the number of anchors? Can I excavate faster? But you are not changing anything. You are just playing with different hypotheses. Then with your client, you agree that if ground conditions are better and are showing from the IoT data that is coming during construction, you already have a plan to change, like, okay, it's better, let's excavate faster, let's reduce the number of anchors. So you can adjust because you plan in advance that. Because sometimes, and I have many examples where we start working in a project that it's almost done in terms of designing, so they are starting the construction. We prove ground conditions are better, but you cannot change anything at that time because all the contracts are set. But if you plan that in advance, you can actually adjust and improve the design and the construction procedure based on the data that you are gathering from your sensors. Absolutely. Reduce anchors, temporary probes, excavate faster, whatever you want, you can do it.
So speaking of the big picture, guys, would you say that machine learning is perhaps the best way and the available right now to take advantage of all the massive amounts of data that are out there?
It is the big challenge when it comes to data management from these projects. Cristian was saying he still uses Excel, and Excel is a valuable tool for very, for detailed or dynamic. And I talk about dynamics, but if we want to change how we analyze data, we can implement that very quickly and easily within Excel. But the overall management of data from large urban transportation or large infrastructure projects is a big challenge. But the value of it is, as I've said, is not necessarily in the immediate, but how we can leverage that within these large language models. And the only way we can do that is to put it into a database that's accessible to anybody who can use it.